All right, so I did my project about predicting birth outcomes for in vitro fertilization using images of embryos. So in vitro fertilization is a modern technique that's really promising. It just has a low success rate and it enables people to get pregnant that want to get pregnant. Related work, people have used deep learning to try to solve this using networks that are similar to Inception and Exception and Stork. They found that data augmentation and preprocessing is essential, and that it's more useful to have data sets of multiple images than data sets of just a single image per embryo for this task of prediction. So radiologists generally look at the cytoplasm of the cell in order to determine the expansion that the cell is going through. And that extent of that expansion will be an indicator for how successful that embryo could be in vitro fertilization. So it's important to look at the PV space and blastocoel capacity. And just generally, we want to look from a 3D perspective, how is the integrity of the cell membrane? So we have a novel data set for this task that consists of 3 labels for an image. So not just did the cell lead to pregnancy or no pregnancy, but also did the cell lead to pregnancy? Did it lead to an unsuccessful pregnancy, to a pregnancy with live birth, or to no pregnancy at all? So it's great that we have this novel data set because of the research we can do, but there's some challenges with the data set in that there's only 1 image per embryo, so we don't have this time-lapse thing, which is proven to be beneficial. We only get 1 cross-section of the cell, and we only have a small number of images. And then furthermore, we have not the greatest data set balance. So you can see in this 3-class distribution, we have very few examples of actual successful pregnancies. So we wanted to perform experiments to try to address these issues and lift our performance on these data sets. Awesome. So I'm just going to give a bit of background before I go into our pre-processing workflow. So we discovered through looking through our data set that there's a hue imbalance in our data set. So some of the images in the data set have a blue hue. And that's because of the lab settings that they were taken in, but we do not want our model to learn based on this. We can see that in the 3-class case, this blue hue is definitely affecting the class and the classification. And we can see that when we train a naive model on this, that data set imbalance is reflected in the model's ability to predict different classes. And this isn't the case for the 2-class case, but it is for the 3-class case. So let's try to fix it. With data preprocessing, we tried 3 things. First, a grayscale and a min-max norm, and a grayscale where we divide each pixel by 255, but we're performing a max norm. And we hope that these grayscale normalization techniques would eliminate the colored issue from our data set and enable our models to get high performance. So we found that we were able to get approximately the same accuracy, but with grayscale and min-max normalization on this 3-class case. So this shows that we're able to train a model that doesn't take advantage of this blue hue in order to make predictions, but that can still predict with high accuracy, and that's great to hear. Next, we experimented with class balancing. You can see that our model never predicts the 0th class. There's all zeros in this column. If we balance our data set such that the model sees an equivalent number of examples from each class, our model becomes much more like it's guessing, but we see that we are able to predict in this 0th class. So that's really good. But there's probably an ideal place where we can represent the fact that pregnancy and live birth isn't the most popular or the most common option, while actually getting the model to learn about all the variations in the data set. So we found that using this practically balanced data set, which isn't completely balanced, the model doesn't see exactly equal numbers of each class, but it's much more similar to being equal than it would be if there was no balance at all. And we see that this enables our model to predict different classes, not just classes 1 and 2, and we're still able to get a really high accuracy. So that's really great. Next, we experiment with data augmentation, and just looking at the saliency map, you can see that our network cares primarily about the center of the image, which is where the center of the embryo would be. And this is exactly what we want to see. This points to the fact that our network is learning something fundamental about our image. Next, regularization, we found an ideal constant, and we can see that our loss curve improves. We found that Inception v3 is the best model for this task based on AUC. And then looking at our best 2-class model, it's doing great with the AUC of 0.4646, which is exactly what we want. And the saliency map looks great. At the center of the image is highlighted, showing that the network really is learning something fundamental about the data set. Looking at the 3-class model, our distribution of examples that we're choosing is pretty good. The model doesn't seem particularly biased by the distribution of the data set, but the saliency map doesn't look great. It appears that the balance in the data set does have some sort of impact on the model's predictions, and the actual content of the image, the embryo, might not be as important as we would want it to be. So future work, we could work with different data augmentation, additional pre-processing, and maybe trying different models like exception and stork. But for now, this is a great benchline to start from. All right, thank you.